we want to check whether two things are close or not. When you have two numbers, we can know two numbers are close or not by subtracting the number and check whether the number is close to 0 or not. Assume that you have two numbers like 4 and 4.1. Then check whether two numbers are close or not. How? Just subtract 4.1 minus 4. That is 0.1. Then 0.1 is pretty small. Then we know that two numbers are close. And you can do the same thing for the n-dimensional points. Assume that you have 2 points in space. Then how can you know 2 points are close? As vectors, we subtract, not just number minus number, but component-wise we subtract and then calculate the distance. Then we can know whether they are close or not. And we want to do the same thing on matrices. When two matrices are given, we want to know whether two matrices are close or not. Why? Because we want to do some iteration and we want to know when to stop. Usually, when two things are similar, we stop, right? When two things are close, we stop. And when you have numbers or vectors or points, then it's possible. But now, we enable it when you have matrices. So this is the idea behind it. And if you have a question, ask. Yes?
When you talk about closeness of matrices, are you talking about point-by-point closeness?
There is no point-by-point because matrices are not points or vectors or anything. Just matrices are matrices. But we regard matrices as like one point. The whole thing as one point in some space. So in some space, matrix is like 1 point. So we are handling the closeness of this matrix and the other matrix. And the whole matrix becomes like 1 point, not the components, but the whole thing. Any other questions? In other words, we have, so let's return back to this part later. So I will save this column. Assume that we have, of course, we are handling the same size matrices. Assume that you have two matrices like this, 1, 2, 3, 4, 1, 1, 2, 2. Are these two matrices close or not? That kind of question. Then how can you answer that these matrices are close or not? And in what sense they are close? That kind of thing should be studied. So matrices are like a point. So in some huge space, matrix is just 1 point. And there are 2 points, right? This and this, there are 2 points. Are these 2 points close in some space? So that is the question. And that's the reason why we are studying different norms. Norms are usually lengths in vectors. When you have a vector, norm of a vector means the length of a vector. So let's define the length, and there is no clear winner. There is no clear winner. When you have a point or when you have two numbers, then there is a clear winner. We can do the difference and do the absolute value, right? Difference, absolute value is the clear winner. What better thing can you expect, right? So whether to check whether two numbers are close. For instance, someone wants to compare my salary and his salary, then check the distance, the difference, right? Check the difference. And if the difference is small enough, then our salaries are similar. It's the clear winner. When you have 2 points in user space, then the distance can be calculated. There is a clear winner. But when matrices are involved, we don't have a clear winner. So instead of using just one measurement, we introduce 3 different measurements. So first measurement is called one norm. Second measurement is called infinity norm. And the third measurement is called two norm. There are 3 popular things that we use. And if you are forced to pick just one, or I was forced to pick one, then I might pick infinity norm. This is the easiest one in practical purpose. But this is not the clear winner. There could be 3 different cases. So do you now see the reason why? Because it's not like numbers or points. Matrices are handled, and we want to check 2 matrices close. Then we want to see the distance between 2 matrices. How? using these things. First of all, one norm is, instead of looking at the formula, look at the simple description. Maximum column sum norm, of course, all the numbers become absolute values. So assume that we have negative signs. I will intentionally add negative numbers, right? I will intentionally add negative numbers here and there, right? So assume that we have these kind of negative numbers, then we drop all the negative numbers in the consideration of the one norm or two norm. And as you can see, one norm is nothing but column sum norm. One norm is the column sum norm. So let's add columns. So add columns. Then if we add columns with absolute value, what is the column sum? And what is the column sum? So let's call this matrix A. Then A matrix one norm equals what? What is bigger? 6. This is the key definition behind this. Key definition behind it is this, and you may check this idea and ask questions. No questions? No questions? So if you look at the description, it is very strange and confusing. But if you look at this word, it's not very difficult, right? Maximum column sum norm with absolute value signs, right? Then now let's calculate the maximum column sum norm of the second matrix B. What is the maximum column sum norm, or one norm of B? One norm of B. To do it, we should calculate the maximum column sum. It is 3, right? With the absolute value signs, right? With absolute. So we have 3. The maximum column sum norm, or one norm, is 3. Then the other direction is possible, right? So the other direction has the name infinity, right? The other direction has name infinity. Then what is the infinity norm of A? And what is the infinity norm of B? To do it, we should add these things with absolute value signs. 3, absolute value signs, it is 7. So the infinity norm is what? 7. Similarly, we have 2 here, we have 4 here, so it is 4. So in this sense, we can clearly calculate the norm of a matrix. Then to check whether A matrix is close to B matrix, what should we do? All we need to do is doing this. A minus B sum norm, right? A minus B sum norm. Do you follow me? We do A minus B, and then check the norm. If the norm is small enough, we say two matrices are close. So let's check A minus B. First of all, what is A minus B? I will write A minus B matrix downstairs. Before writing it, I will write the A minus B matrix and then write the norm. A minus B matrix is component-wise subtraction gives us 2. Component-wise subtraction, component-wise subtraction, component-wise subtraction, 2. And this is the case. Then A minus B one norm is A minus B one norm is like doing this column sum, absolute value column sum, right? So A minus B norm is 5. Do you follow me? And similarly, A minus B infinity norm is done 5, 3. Do we get this kind of result all the time, or it's just coincidence? It's not always the case, right? As you saw in the previous case, right? Row sum norm and column sum norm might have no relation, no straightforward direct relation. Somehow, we may get the same number, but it's coincidence, it's not general rule. So in any case, once you have a matrix, we can determine the one norm and two norm, and using these norms, we can check whether two matrices are close. In what sense? In one norm sense, what is the closeness of A and B? 5, right? In infinite norm sense, 5. So in what sense are they close? We ask questions. And in the future, like chapter 6, we will generalize these ideas to not just matrices, but random functions. But we are just beginning to study abstract concepts. So we are not just handling space of points or numbers. We are handling space of matrices. So matrices are just points in this space. Then you should know whether they are close or not by using this idea. In what sense? In what sense? So do you clearly get the picture? Then the final thing is the two norm. Two norm is maximum sized eigenvalue of A star and A, and I will define A star briefly. And that absolute value is square root, so it's very complicated, right? Let's do it. A matrix is given. So in usual sense, I will use C matrix instead of A, B are used, so I don't want to confuse you. So I will use C matrix. The complex matrix, 1 plus I, and then 2I, and then 2 minus 3I plus 4. This is a matrix C. Then we consider the transpose of this matrix, and transpose of the matrix is written in this form. Transpose is this. When you transpose a matrix, the first row becomes the first column. This first row becomes the first column. So what is it? 1 plus I, 2I. And second row becomes second column, and so on. So this is the transpose of a matrix. This is the definition. Now, we add one more thing to this one. That is over bar, right? Upper line. Upper line represents conjugate. So we conjugate it, then plus I becomes negative I. So 1 plus I becomes 1 minus I. 2 minus 3I becomes what? I becomes negative I. So 2 minus 3I becomes what? 2 plus 3I. 2I becomes what? Minus 2I. 4 does not change. So this is the conjugate, right? So any I becomes negative I. This is the conjugate. And in one notation, we use star. We use star. This is the star expression. So it's the transpose of a complex conjugate. Any questions? In real case, in real matrix case, we don't have any I. In other words, conjugate do not change anything in real case. So in real case, the same as transpose. So let's now handle the case C and find the eigen value to determine the norm. So I will use C. So let's do I will go up and show you the definition one more time. The definition is here, right? It is A star multiplied by A, right? A star multiplied by A, and then the maximum sized eigenvalue. Maximum sized eigenvalue and absolute value of that square. So first thing first, I will do this, and then I will find the eigenvalue, and then take a square root. So C star multiplied by C equals 1 minus I, 2 plus 3I, minus 2I, 4 multiplied by C, given the upstairs, 1 plus I, and then 2I, 2 minus 3I, 4. So instead of doing hand calculation, let's do these things with MATLAB. Of course, MATLAB isn't the only one, but it's the convenient one you can use. And in my opinion, almost all of you have used MATLAB. So let's use MATLAB. I will define C first. C equals 1 plus I and 2I. Second row is 2 minus 3I and 4. So this is the matrix, right? This is the C matrix. Do you know how to do this complex conjugate in MATLAB? C what? C star? C is the transpose. This is the transpose. I know the transpose, but maybe conjugate work. Right? No. In any case, I will just type it because I don't know the command. C star, right? C star, it will be defined here. C star is complex conjugate of this thing, then 1 plus I, and then minus 2 times I, and then 2 plus 3 times I, and then 4. I typed C star and C. Of course, if you know a command, then you can use a command. Then let's do the calculation. C star multiplied by C is given here. So this is the matrix. Then now, this is very strange. Why do we get I see. So I might make the mistake, right? C star is defined this way, right? Let's go back to 1 minus I, and these are wrong. What did I think? 1 minus I, and then 2 plus 3I, completely wrong. I do not know why I did these things. 2 plus 3I, and then so I'm just typing C star, and then minus 2I and 4, minus 2I and 4. So I correctly typed C star. And now let's do it one more time. C star multiply C. Still strange. Is something wrong? Let's type C star and C. C star is 1 minus I, 2 plus 3I. Negative 2I, and then 4. Is C star correct or not? Right. This is the first column. This is the second column. This is C star, right? This is C star. And now C, is C correct? I think they are correct, but C star multiplied by C is very strange. Really? Let's check. That might mean component-wise multiplication, right? But here we are doing matrix multiplication. So this should be correct. But strange thing is this, why do we get these complex numbers? I expected. So let's return back to our definition. So this is the definition, and I copied the definition correctly. And then I wrote the conjugate of this thing here and conjugate of this thing here. Everything looked correct. Be my misconception, but let's finalize the deal. And C star is here. C star is 1 minus 1 negative 2i, and then 2 plus 3i and 4. And then C is here. 1 plus I, 2 minus 3i, and then 2i and 4. So what, I guess this is the best thing we can get, right? And now we want to get the eigenvalue of these things. So eigenvalue of, that's called, I want to get the real things, real numbers instead of imaginary numbers. But that does not matter. Let's get the eigenvalue of this matrix product, right? So there are two eigenvalues. Square root of 0.1147 and then 34. So what is the maximum of 2? 34 point something, right? Then, because of this calculation, square root of this value, right? Second value, right? 34.8853. This is the norm of the given matrix C. So it's a little bit complicated. So if you have a question, ask me. In any case, I'm showing you a very strange case, but it may not be this strange in general. So we are calculating the eigenvalue of this product matrix, yes? So we multiply two matrices, and then we determine the eigenvalue. There are eigenvalues, right? There could be one eigenvalue, 2, 3, 4. And then among these eigenvalues, we pick the biggest one with absolute value, right? So 34 was chosen, and then square root of that is the length. So in this case, the length or norm of the matrix C is 5.9, right? 5.9 is the norm. Because of this reason, C matrix 2 norm, right? C matrix 2 norm is approximately equal to 5.9. Of course, if there is any mistake, then you can correct it. But roughly, I'm giving you the idea of the 2 norm. So 2 norm is rarely used. It is theoretical norm. It is rarely used because of this complexity. Any questions? Then let's return back to the definition part and check whether you completely understand the idea. First of all, matrix is given, and we have general size matrix. Then we can do the column sum norm, right? Column sum norm to determine the one norm, or row sum norm to determine infinity matrix, right? And we can determine the two norm. Then let's do easier example. Assume that you have a matrix like this. is what is the size of this matrix? Yeah, size of this matrix. 1 by 2 matrix, right? 1 row by 2 columns. Then assume that this is A, I will say A, so I will say D. Then what is the D star matrix? 1, 2, right? D star matrix. Then D star matrix multiplied by D matrix is what? Equals 1, 2, 2, 4, right? Then let's use MATLAB to do the calculation. So MATLAB helps us. D matrix, DD matrix is 1, 2, 2, 4, right? This is the DD matrix. Then DD matrix eigenvalue is 0 and 5. 0 and 5. What is bigger of the two? 5. So we take the square root of this bigger number. So the length of this D matrix is, or norm of this, 2 norm of this matrix is square root of 5. Do you follow me or not? So this is the way to find the norm. Now it's your chance to do the calculation. Assume that E is given in this form. What is the size of this matrix? Size of this matrix is what? 2 by 1. Then please find the norm of this matrix. So we get the result, right? So in general, when you have a row vector or column vector, and we apply 2 norm in any way, we get the same result. The intermediate calculation may look very different, but the end result should be the same. We can even prove this fact. It's not coincidence, it's a general fact. So when you have a column or row vector, no problem. And what is your real sense? 1, 2 vector. What is the length of 1, 2 vector? Square root of 5, right? By Pythagorean theorem, right? Square root of 5 is. If you doubt it, you can check by using 3, 5. So 3, 5 matrix might be the one that you can consider. So assume that you have F matrix, 3, 5. Then what is your general sense of the length? What is the length of this vector? 5, right? So let's do it. Let's do the calculation. 3, 4 multiplied by 3, 4 gives us this thing, right? Then let's call this DD, FF matrix, right? FF matrix is this one. Then eigenvalue of this FF matrix is what? This one. Then what is the square root of 25? 5, right? We get 5. Or the other way, then you get 25 and the square root. Any questions? So when you, yes?
The first two were the 1 norm and the infinity norm. We're just using those for comparison purposes, but we're using this for length or size.
vector case, it is called Euclidean length, and in real length, but if it is matrix, also it loses any meaning in its straightforward meaning. When we handle matrices having more than one row, then we lose the meaning, one row or one column. So sometimes norms have straightforward meaning, sometimes norms do not. And in fact, you asked a nice question, and this is the situation. Assume that we use one norm in vector case. Usually, we get this kind of shape, satisfying the condition that the one norm is less than or equal to 1. In other words, what is the area satisfying this? What are the vectors satisfying this are contained in this diamond? If we use one norm. If we use two norms, and then say that the vector contained inside 1, right? The length of the vector is less than 1, is contained in this circle. And if we use infinity norm, then the meaning is this, right? So depending on norms, we have different boundaries. Essentially, all of this can represent the same closeness. In other words, if we make the rectangle small, right? If we make the rectangle small, then we contain everything inside small area. In other words, they are close enough. If we make the circle small, then we can contain everything in small area. If we make the diameter small, then we can contain everything. If we sketch all these things in one plane, then they look like this. One here, right? This is one. And then circle. And then diamond, right? So if one is close by one norm, right? One doesn't mean real one norm, but by a norm, then it is close by the other norms too, right? If they are close enough in this norm, then they are close enough using the other norm. For instance, if we use diamond norm, then we can consider a little bit relaxed norm, right? This kind of. In other words, if one is inside one shape, then even if we use other norms, they might be already close enough. But this is too abstract. These kinds of things are handled in metric space or topology, but we don't want to go into that kind of. But roughly, we are just doing the actual calculation. We are doing actual calculation to check whether two matrices are close or not. Two things are close or not. Two numbers are close or not. Two points are close or not. Usually two vectors. Or two matrices are close or not. And you use the norms. So in my opinion, I completely covered the matrix computation. And please browse these things and ask questions. And if you need more examples, then I can give you plenty of examples. Yes.
Think of a practical application where we
I see. In fact, in the future, we will cover the matrices handling. It's not used in this section directly, in this chapter directly, but in the future chapters, we will handle the closeness of usually vectors. The vectors are in other words, good observation. We will generate matrix A2 from matrix 1 by iteration or something, right? And we can generate this kind of thing. And then we want to know when to stop. When to stop. then how can we set the criterion of stopping? When two matrices are close, we may stop. Then how can you check two matrices are close? So you will see these things in advanced study, especially linear algebra section might be the one. So, in my opinion, all of you completely understand the definitions and calculation, and at the same time, the meaning. Closeness, right? They are close. In the past, this section was given because of the programming reason, because it's not easy to program to do the matrix handling, multiplying matrices or doing calculation with matrix were difficult in the past. For instance, assume that you are using Fortran or even C. How can you multiply two matrices? How can you multiply two complex matrices? It's very tough to program. But now, many people use MATLAB, and as you saw in MATLAB, you don't even have to program anything, just type, and then you can get the result. But still, there might be some people having hard time using different packages. For instance, Maple had difficulties because they didn't develop built-in matrix handling or complex number handling. I guess complex number handling was embedded there, but built-in matrix handling was not there. So, for instance, one uses this package, the other is the other package, and they create programs that they are not compatible. Sometimes calling the other may cause some trouble in Maple. But MATLAB, these things were all built in. But in any case, some of you may still use different packages than MATLAB and may have a hard time in this section, in this chapter, I mean, because how to really program these kind of things. Transposition or conjugate or multiplication. It's not easy, right? So this is the reason why I relaxed this chapter to just norms. But to some people here, you should handle matrices using your languages, your programming tools. How many of you don't use MATLAB? You use Mathematica is wonderful. They can handle way better than all others. In fact, the CU system recently made a deal with the Mathematica company, Wolfram Research, and I guess students can use Mathematica on campus. I do not know whether you can download and then use the software at home or something. You may check that. And Mathematica is a nice one. In any case, this is the reason why this chapter is the shortest. Not because of the norm, but because of the complexity in handling matrices. Unlike numbers, it's difficult to handle matrices in programming setting. But in any case, I covered the important part, and if you have a question, ask. Then let's go to the next chapter. We are faster. So the next chapter is systems handling. Now, you will see the reason why we are defining these kind of strange things, and instead of jumping into the actual things, I will describe the overall situation. We want to solve equations with, I will use matrix form. First order relations. So assume that you are solving this kind of system of linear relations, right? We don't have any squared terms in x1 or x2 or xk or xn, just linear order terms. Then how to solve this kind of thing is very, very important. Believe it or not, when you look at all screens or TV monitor or things, these kind of things run behind the technology, especially when you use cell phone, right? Cell phone, or when you watch TV, monitor screen, figure, all the technology use this basic thing. So it's used every day, and it's very, very important. So when we have just a few unknowns, it's not very tough. But what I am saying is not just a few unknowns. Assume that we have 1 million unknowns. To solve for 1 million unknowns, we need to solve a system of 1 million equations. Then how many coefficients are there in 1 million equations? How many coefficients? Trillion unknowns. So we are handling these kind of things. But to theoretically cover these things, I will introduce the idea using small number of unknowns. But you should not just say, oh, why should we use different way than this way? So there is a reason, because we are handling huge matrices. But in any case, let's use small matrices to handle the case. Assume that you are solving this kind of equation. So assume that you are solving these kind of equations. Then how to do it? How to do it is a question. And the idea that I want to explain is this one. Oh, we want to eliminate this one. How? We multiply top one by 2 and subtract. If we multiply top one and subtract, what happens? If we multiply top one, then it is 10x1 plus 12x2 and then 22. If we subtract, Then 10 minus 3, that is 7. 22 minus 15, 7. So x1 is 1. And then afterwards, you can get x2. So this is the algebra that you learned in maybe high school or middle school. But here, we need a strategy that is more systematic than just ad hoc approach. So I will talk about systematic approach. And the first approach that I want to explain was found by Gauss. And he used elimination idea. Assume that we are solving an equation. Then first of all, we eliminate the x1 term in the huge number of equations. In this case, only 2 equations, so at least 1 equation we want to eliminate x1. So he used, for instance, the first equation as pivot, and this is the pivot, and use this pivot to eliminate this one. And how can you eliminate it? How can you eliminate it? The elimination is possible by doing this. So for convenience, I will call this row 1, right? Row 1. And I call this row 2. So we can do this thing. Row 2 minus 5 3/5, right? 3/5 row 1. 3/5 row 1. 3/5 row 1 will eliminate this number. Do you follow me? Row 2 minus 3/5 row 1 will eliminate this number. So this is the idea. So let's really do the calculation. 3/5 times row 1 is what? 3/5 row 1. So I will write 3/5 row 1. 3/5 row 1 is 3/5 multiplied here is 3x1. 3/5 row 1 is 18/5 x3, x2, and 3/5 row 1. So this is the 3/5 row 1. I multiplied row 1 by 3/5. And now let's do the subtraction. From what to what? From this, right? From R2 we subtract this thing. So we do the elimination. And as you can see, we will get 0, and then plus 12 minus 18/5 x2, and then 15 minus 33/5. This is the result that we will get. Then let's do the calculation. (12 minus 18/5 is 8.4, right? 15 minus 33/5 is 8.4. 8.4, 8.4. So what is x2? x2 equals 1. Because of this, x2 equals 1. Because x2 is equal to 1, I can plug this back in. I can plug this back into the equation. So x2 equals 1 comes into this place. Then what happens? I will use this place. 5x1 plus 6 times 1 equals 11, or if we rewrite 5x1 equals 11 minus 6 times 1. Then it is 11 minus 6, or 5. So if I divide both sides by 5, it is 1. So we get the solution in this world. So take a look. When you do the elimination, we eliminate from the top, right? From the top. When you do the actual finding of solution, we start from the bottom, right? We find the last unknown first, and then go up. So we have special name. This direction is called the forward elimination. This direction is back substitution. Back substitution. The forward elimination and back substitution are combined together in Gauss elimination method. So to make sure the idea behind these things, I will give you 3 by 3 case. Because of the usage of the column, I will copy and move these stuffs. I still do not know how to grab these things and then drag these things. Very tough to drag these. I lose all the, there might be some. Great. What's that? Did I lose? I completely lost. Oh no. I messed up. There is no undo. It's very strange. In the strange. In any case, we now know how to do it. Then let's do it with 3 by 3 case. So you may pick any number. I didn't make this up. So you may pick any number for the coefficients x1, x2, x3 equals something. So you may pick any number here. x1, x2, x3. So what number would you like? Do you like? So what number do you like? What did you say? 4 and then? 4 and then plus 3 and then plus 5 and then 12, right? It's obvious. 2 and then 5 and then 6, right? So please solve these problems on your own using the same idea. Then you will see whether you completely understand the idea or not. So the goal is not solving this by hand, but at least you will get the idea of these things by doing the actual elimination. I'm writing the necessary steps that you need to do in order. So did you get these two first steps? So you should have done these two steps. I did the elimination, so I removed the 4. After removing 4, I removed the 2. I did the elimination of the first column. Other than the top pivot column, I removed everything downstairs. So that's the strategy of Gauss, right? Gauss developed this idea. Eliminate everything underneath. Then the next thing is eliminating this column. So we use this as pivot and eliminate this one. So we calculate this value and calculate this value and then consider the ratio and then eliminate this value. That's the strategy. So I will do the ratio calculation. (5 minus 14 over 3) divided by 3 minus 28 over 3 should be equal to this, right? Can you do fraction representation? Do you know how to do fraction representation of this kind of thing? I will do it directly. Yeah, I will do it directly instead of, because as you can see, if we simplify, let's simplify the first one, then it is 9 minus 28, so minus 17 over 3x2, and this is 17 x3, and this is about 36 minus 4. 36 minus 4 is what? 32 over 3. And similarly here, it is negative 1/3 x2, and then 12x3, and then 39 minus 2, that is 37 over 3, right? So we can do the calculation straightforward. Then the factor is clear, right? We can multiply the row here. Let's call this row 2. Oh, this is the 19, right? Thank you. Row 2, right? And then row 3. Let's call this row 2 and both new row 2 and row 3. Then what should we do here? Row 3 is subtracted by row 2 times the ratio. The ratio is minus 1 over 19. Right? So we should do these things. Of course, there's an easier way than these things, but we are not really solving these things by hand calculation. We are creating some algorithm to handle the problem. The hand calculation might be messy, but actual calculation doesn't involve this kind. In any case, we are doing this thing, right? Row 3 multiplied by, row 3 subtracted by this row multiplied by negative 1 over 19. Then we can eliminate this number. And then we can do the same thing. And what is it? It is 12 minus 17 multiplied by 1 over 19, right? x3, and then the same thing, 37 over 3 minus 32 over 3 multiplied by 1 over 19. So this is it. So we now eliminated everything in the second column. By the first 2 steps, we eliminate the first column. By this step, we eliminate the second column. Then, what is it? Let's do the calculation using MATLAB. 12 minus 17 over 19 equals this one. And then the right-hand side, 37 over 3 minus 32 over 3 multiply 1 over 19. 11 over this, right? You get different things? Is there any mistake? Can you find any mistake? Oh, I see, I see. This should be plus, right? So both should be plus. Only first thing is because of the math. Sorry. Thank you very much for the correction. So let's recalculate it. Plus, right? Plus here. And plus here. And as you can see, you get the same numbers, right? You get the same numbers here and here. You get the same numbers. The coefficients and the constants are the same. So because of this, x3 is what? x3 is 1. And then, now we are doing back substitution, right? We are doing back substitution. So we found x3, then we use this thing to this place, right? This result should be used in this place, back substitution. Then what do we get? I will use the right side column. Minus 19 over 3 x2 plus 17 times x3 equals 32 over 3. But it is good to use it on the right hand side, right? So 17 times 1. Right? So let's do the calculation. Then this is equal to 32 over 3 minus, this is 51 over 3. Then it is minus 19 over 3. So now can you find x2? x2 is what? 1, right? x2 is found. Now we do the back substitution. So we do the back substitution to the first equation. Back substitution to the first equation. So we replace x3 by 1, x2 by 1. Then what is x1? 3x1 equals 1 minus 7 times 1, and then minus negative 9 times 1. And if we do the calculation, 1 minus 7 plus 9 equals 3. So x1 equals 1. So we have found these things in back order. So do you clearly see the idea of forward elimination and back substitution? So this is the Gaussian elimination method. So let's consider the general equation instead of this specific case. But if you have a question, ask me. But as you can see, it is very inconvenient to use x1, x2, and so on. So in the future, instead of writing down everything in this form, we will just extract the coefficient. In other words, in the previous case, what coefficient did I use? I used 3, 7, negative 9. 3, 7, negative 9, and then 1. I used these things in the past, right? But instead of writing all these things, we can just say 3, 7, and then negative 9, and then 1, right? Then it's very easier. So we can write the problem using matrices instead of the whole equalities. In any case, this is not the direction we should follow right away. So we will just delay this kind of development, but the idea will be explained. The idea is simple. We have a matrix or problem like this. Then we have following lines, right? We have the following lines. Then what you do first is eliminating all the numbers here. In other words, we will have just 0 here, 0. We make these equal to 0. Then because of this 0 change, we may have changed here, right? We may have changed here, like the one that you saw, right? Because of this elimination, we have changes here. We didn't change this pivot line, but we have changes everywhere except the first line. And then, now the situation is the same with the smaller scale. We are now focusing on these problems instead of the full problem. Then it's exactly the same situation, right? Now we regard this as A11, and then do the same thing. Then we eliminate all these numbers, right? We eliminate all these numbers. Then we now reduce the problem to this size. And then now we regard this as A11 and do the same thing, right? In general setting, we can do the same thing and eliminate everything down underneath. And then we regard the smaller problem, right? We regard the smaller size problem, and then we regard this as as A11, like the one here, and then eliminate everything down underneath, right? Everything underneath. Then we consider the smaller size problem. So we always do the same thing. Then, as you can see, we'll get this kind of shape. If we complete the elimination steps, then we will have this kind of pattern. All the numbers below are 0, right? All the numbers below this line is 0. Eventually get this step, and then finally only one number here, right? One number here on the right hand side. You follow me? So this is the steps. These are the steps necessary in the forward elimination. In other words, everything underneath becomes 0 in the first pass, second pass, third pass, fourth pass, and so on, and eventually we get zeros here. And while we make these zeros, we get some changes in the coefficients, right? We get some changes in the coefficients. So we go all the way down. Once we go down to just one number, this means xn times some number, right? Xn times 5 equals something, right? That kind of, then we can calculate xn by doing simple division, right? By doing the division, we get the number. Then we substitute this in. Then we now know this number, but we don't know the previous number. So we can solve this equality for the only unknown number to find it. Then we know two numbers. Then we plug in two numbers, then we can determine their number. And we now know three numbers. Then we use three numbers to determine the number. So we do the back substitution all the way up to find everything. So this is the idea. And next time, I will mention about the idea of really programming these things, not just doing hand calculation. So if you have questions or difficulties, you can approach and ask me.